We've completed prompt 1 and we've completed prompt 3. Let's write functions for our plans. Plan L is mostly done. We've already established how to express $50 per month. How should we express $50 per month each year? How should we write it algebraically? Your previous experience with algebra should translate it as 50 multiplied by 12 multiplied by y, where y represents the number of years. There's a dozen different ways to write this hooey bluey, so please pardon me if I don't write it the way you want it. What matters is our mutual understanding that the yearly value is the ingredient that demands the most attention. Once we set up the recipe, set up the function, a computer can do the rest of the cooking. It's such an old, such a useful, such a beautiful way of thinking that people have over-dissected it and argue over the names of the components. Take it easy, you don't need a black belt in functions. No need to memorize the terms. Learn by example. Seek a practical understanding. When I write this, it's a fancy way of saying Plan L after 18 years at $50 each month will be $10,800. This L18 stuff is just clarification. You take that number and you plug it into the formula. It's y to y, so I take this 18 and I'm going to plug it in here, do the math, get the result. If the input is 2, you put in 2. If the input is -7, you inject -7. It's read, by the way, if x is -7, then a function of x when 50 times 12 times x is -4,200. You notice that I altered the y variable to x, the sign for multiplication, and the capitalization of L? Good eye! Did you also notice how it doesn't change our bottom line? Now if I were to alter this input to A as in Apache, and this variable to P as in Pawnee, I'd be doing a mathematical sin. For our purposes, they must be the same. Normally at this point I present you with a handful of other exercises with other functions, but I doubt I have that kind of time with you. We need to go further and deeper to answer the prompt. Therefore, if you need more practice, pause this video and find some online. Functions are terrific for charting. They are the recipe to do it. I'm in the graphing software GeoGebra, by the way. I'll plot our function L. L of x. GeoGebra insists the domain, the input, be x, because it uses that to generate the range, the output, as a y value. So back to our function, L of x equals parentheses 50 times 12 parentheses, close parentheses, x. I hit enter. I don't want the color to be blue. I want the color to be orange. And there, we've plotted our function. Now we might not need a plot in order to calculate when x is 1. 1 times 600 is going to be 600. However, the point here is to realize how much better a graph is for predicting the output. When x equals 2, we don't even have to calculate, we can just look. It's going to be 1200. When x equals 3, I'm going to zoom out, move it over. When x is 3, it's going to be 1800. If you're the type who doesn't like to compute, then graphing functions is for you. Watch this. Our function L of x, when x is, we'll just do 3 to prove it, 1800. When L is, let's say, 100, it's going to be 6,000. When L is, what did we say earlier, -7, close parentheses, -4,200. Freeze. This is another point at which I'd normally stop for exercise. Sorry, we're moving on. We label functions so we can compare them. We could compare our function L to something out of the blue, like this function, I'm calling it Q, or this function, I've named it R. Yes, functions can be exponential too. However, our concern is to compare it to plan E. How would we write the function for plan E? Let's pause on that thought. To answer the prompt, we need to recall the categorical difference between plan L and Plan E. What is it? What makes them significantly different? Here's a hint. Plan L is increasing at a constant pace, whereas Plan E is increasing by interest on interest. Plan L is what type of function? Yeah, that's right, a linear function, whereas Plan E is a exponential one. Yes, that's why I labeled them L and E. You're so smart. You've likely been quizzed before in deriving a function based upon a table of data. If so, buried deep in your memory is the key to doing so, both with linear functions and with exponential functions. Can you remember the key? I couldn't. I had to look it up. It has to do with finding the change between outcomes. You recall Plan L is increasing by 600 annually, but how is Plan E changing between years? Look at how we determine change in Plan L. Don't let the notation fool you. It's just a fancy way of saying take the balance of any given year and subtract the balance of the previous year. For example, 3,000 minus 2,400 is 600. Let's try that on E. And with our spreadsheet powers, it makes it easy. We're going to go equals. We're going to find the amount of change between this year and this year. Now you might be saying, Ash, why did you skip year one? Why did you skip this number right here? That's because they're starting with a balance of 1,500, and that 1,500 is going to skew the relationship that's going on right here. That's why I skipped it, or I omitted it. So we're going to take this, and then we fill it down so that we don't have to type it in. It's not constant, though we knew that because it's an exponential function. What else should we try? Is your brain whispering divide? Yeah, I sense it too, because multiplication is the mathematical cousin of addition. Then, we reason, the kin of subtraction is division. Let's try dividing. Okay, same thing, except this time we're dividing. So we're going to take, not this number, that's the change. We're going to take the balance, divided by, in the computer we use a slash to represent division, divided by that number, 1.076. Okay, now I'm going to go down and fill down. Control D is in delta. They're all 1.076. It's a constant. That's more like it. You'll probably deduce how this 1.076 applies, but for now, let's focus on continuing to generate a function for Plan E. Suppose the way forward is dim. You're at a loss for what to do. Don't despair. Try it out on graphing software. Okay, here we go.
In this hyperstate, we'll try all the many configurations of our puzzle pieces, 1500 and 1.076 in variable x. At the speed of thought, I've tried every combination and it's still not functioning. Functioning, get it? Guess I have to slow down and think. Think.
Let's go back to this anatomy of a function slide. We're trying to write a function for Plan E. We've got a label, we've got an input, and I've contemplated all the various permutations of the parameters with the variable x. My algebra instincts tell me it's 1500 times 1.076, but the rest... That's it. Plan E is an exponential function. The variable will be an exponent. Okay, so let's test our function out. E of x equals 1500 times 1.076 to the x power. I can't see it. Why can't I see it? I can't see it because I need the scale of my graph is not even starting at 1500. It's off. So I'm going to move this over and I'm going to adjust the scale. I have to adjust it really heavily. There we go. How did I type this into the computer? I typed it using the exponent. I achieved the exponent by using the caret key, which you would get by pressing Shift 6. It looks like a little mountain top. We can verify this, naturally, by entering our data table as a list of points. So I'll select our data table for Plan E, and I'm going to use the List of Points tool. what it's going to do is it's going to treat these as x coordinates and these as y coordinates. X and a y, x and a y. That's what this menu wizard is showing me. If the points fall on our plotted function, then the function we've written is legit.
Here, I'll even do it for plan L. Can I do the list of points? Gives me the wizard. Thanks. There's our points. There's the line. Bam.
We've answered the second prompt. Good job. I'll devote the rest of the video further clarifying the function of plan E, how to make sense of it. We'll be deep in the weeds, so I won't be offended if you skip ahead to the compound interest formula. Let's investigate our function for plan E. Let's make sense of the parameter 1.076. The scenario was saving $1,500 at 7.6% interest, not 107.6%. Emphasis on 100. What is going on? Remember our original formula for plan E? It was an alteration of the basic simple interest formula we were familiar with. We altered it by A, omitting the time component because we were manually accounting for one period, that is each year, as a line item on the spreadsheet. B, choosing less confusing language by renaming the principal to balance. And C, most importantly, adding the interest to the balance. This becomes the interest and we added it to the balance. In short, that's what we did for each year. We compounded it manually by adding interest each year to the balance. Let's zoom to just year 1. If the beginning balance is $1,500, then the interest will be 7.6% of that. We add the interest, which was $114, and the balance becomes $1,614, just like old times. Now, the 1 in the 1.076 comes from some nifty algebra. We can rearrange the equation by expressing this 1,500 as 100%, because 100% of 1,500 is 1,500. To do that, though, we have to rearrange our signs as shown. This is multiplication. Let me simplify this to prove that the result is the same outcome. 1,614 for year 1. Year 1 is 1,614. That algebra trick, by the way, is called the identity and distributive properties. That's right. All the algebra you thought was senseless is now haunting you. I know it's been a while, so here's a more explicit repeat. I've changed the percent to a decimal, then calculated the same 1,614, just like old times. But we can rearrange the equation using the identity property. It seems silly at first until we combine that technique with the distributive property. We simplify to get the same result. I wondered if this math was robust, if it would always work. Here's another example. And here's that example visualized. I believe the answer to my question, does this always work, is yes, though I haven't tried it with every number. Here's a challenge. Can you find an exception? For those of you still wondering why our variable must be an exponent, it's a simplification of the constant change each period. In this case, the balance is increasing by a multiple of 1.076 each year. When we multiply by the same thing repeatedly, what is that called? Recall back to your algebra basics. 2 times 2 times 2, for instance, is 2 to the third power, right? Well, 1.076 thrice times itself will be 1.076 exponent 3. Thanks to mathsisfun.com for this eloquent explanation. Please keep in mind this third power is only good for year 3. It won't calculate the balance for year 4, year 5, or year 18. Thus, we use a variable like y as substitute for whatever number we need. So what's the most important thing among all this to remember? When trying to write a function based upon data, whether they be points on a graph or in a table like this, find the pattern in the data by calculating the change in each measurement. That's the key. For linear functions, subtract. In other words, find the slope of the line. For exponential functions, divide.